Hey, John here. Let's talk about copy constructors. Now, before we get into all the nuances and details, let's make sure we understand what we mean by a member-wise copy. Okay, this class right here in the demonstration, the first program I write here, will do a member-wise copy of this foo object. Let's see what this thing is. It's a variation of what we've seen before. We've got two private member variables here. We got a couple of constructors. We have a destructor, all of which print out messages so we can see when they've been invoked. We've got mutators and accessors that just simply allow us to get in there and touch the member variables. And I've added a dump routine down here to allow us to write more terse code down here in main. We see a little bit easier to see what's going on, okay? The dump routine simply says, hi, I'm the foo dump function with the address of the object and a message that you can pass into the dump routine up here that it puts in square brackets. Then it just simply prints out all the member variables, okay? So here's what we got going on down here. Main creates a foo. He's going to call it F1. He sets the two member variables in 99 and 88. We're going to dump out its contents like this with a little message that says F1. We then print a row of asterisks. We create an F2, and we're going to say, make me an F2 by copying the contents of F1 into F2 when it is constructed. All right. Then we're going to set B, and we're going to dump out F2, and then we're going to dump out F1 again when we're done, just to prove that we haven't modified the contents of F1 when we constructed F2 right here. All right, so let's go ahead and compile it and run it and see what we get. So here we go. We've constructed the first one at address that ends in 3B0. And we set its values to 99 and 88, as you saw. And then we call the dump routine. So the dump routine says, hi, I'm dumping the one that with an address that ends in 3B0. The message is F1, and we can see the values. All right. We then create an F2 object that's a copy of F1. And we dump that out. Now notice that there was no messages from any constructors in here. Yet we have an F2. It has a completely different address than at F1. This one is at 3B0. This one's at 3B8. And we discussed before, this particular object has 8 bytes in it because it has 2 ints. Each int is 4 bytes. So it makes sense if they happen to be sitting next to each other in memory that they'd be 8 bytes apart. That's just a coincidence, because they're both local variables, all right? The F2 object instance mysteriously gets constructed, and we can clearly see that the F2 variables are what we expect them to be, the 99 and the 4444, because we called the mutator on B and changed it. And after we call dump on F2, we then call dump on F1, which you can see is still at 3B0, and nobody moved it anywhere. And we can see its contents are the same as they were originally, again, as we expect them to be. Then we go out of scope because we return, and they're both destructed in the opposite order that they were constructed, all right? So this is all straightforward and makes sense, except for the fact that how in the heck did this thing get constructed if it didn't use our constructors? Well, the answer to that lies in the fact that there's a default constructor that is what we call a copy constructor. So here's a copy constructor. It looks like this. We did not provide one in the last example program. We are in this one. A copy constructor takes a constant reference to an object of the same type and is just a constructor like these other ones, okay? So what is this one going to do? It's going to print out, hi, I'm here. It's going to print a different message than these other ones do. It's going to print out this just like the other guys up here do. And it's also going to print out the address of the object that we got a reference to up here. You remember that ampersand F here is the address of F. This one up here simply says, I want F to be a reference or an alias of the foo that I'm making a copy of while constructing a new foo. All right, so look and see what's going on in here. I can just take ampersand F because it's just a variable like anything else. I can say F.A, F.B, Foo is a member, it's a constructor of the class foo. Therefore, it has all rights and privileges to access the private parts of any foo, not just itself. So he can reach over and grab f.a and make a copy of it. You can reach over and grab f.b and make a copy of it. This copy constructor here, other than the fact that it prints out this message right there, is doing the same thing that the member-wise copy does by default. And that is, it just goes over and grabs the A, copies it over and grabs the B, all right? If you scroll down here, we see no real changes to the rest of the code. In fact, let's go ahead and diff them so that we're all clear exactly on what changed. Copy 1 versus number 2. Those the only difference is I've added this constructor, all right? So let's go ahead and make that. I guess it's already compiled. Let's run version 2 here. Let's give ourselves a clean screen here. Okay, running version 2. So it comes along and says, hi, I'm making the first local variable called f1. It's going to get stored at 04B0. Okay, and we recognize that. This time we can see, oh, it used the copy constructor. Well, that's why we didn't see it before, because it used the default one. Now it uses the explicit one that we wrote, and we read this by saying, I'm building a foo. This is the signature of a copy constructor. This is the this of the constructor, just like everybody else is up there. So this one's going to go at 4B8. And ampersand F is 4B0. So you can see here that the F variable over here that we're grabbing a reference to at this address is the F1. So we're getting a reference to the F1 while we're constructing what will be F2 down here. Then we dump out F2. We can see the 04B8 is the one for F2. And then we dump out F1 again, and that's located at 4B0, which is the one that we got there, and the one that's up there, and everything else is the same, all right? Okay, now that we got a copy constructor, and we know right there, we know that it is called. When we make a copy of something like we did right here, we can dump that all out. Let's add some other stuff here. Look what's happening here. This func F2. What happens when we call a subroutine like func here? Scroll too far. And we pass it a copy of foo. We pass it foo by value. All right. This is not a reference to V. This is not a pointer to some class called V. No, it's a copy of F2. So our copy constructor will be called in order to make a copy of F2 in order to call this func function right here. And again, we'll call it again and send it a copy of F1 down here. I suppose what I should have done is modified it inside here to show us that we are not modifying our copies that are in the caller, right? So if I say v dot set B to whatever, 7777, and it will then show us that we didn't destroy these guys and we passed them in by copy. That was probably a bad example. No, it's a good example. All right, so let's run copycon 3. Let's see what we got. What do? We do the same thing we did first time. We create one of these called F1 and dump it out. We make a copy of it called F2 and we dump that one out. All right, no changes there. Now we move along, and what are we doing now? We're making what? We're making another copy because we passed. What do? We're making a copy of the item here at 150. That is F2. We can see that up here because we passed F2 by value into this function that took a foo object by value. All right. So there's why the compiler snuck in a copy. So the copy could be passed to foo. Foo then modifies it. You can see the 777 down there. It then returns, and we see the destructor being called on 3158, which is the copy that it made, so that you have a temporary copy during the call to the foo function. All right, we then call the function again. As you know, the second time we called it, we passed it a copy of F1, and you can see the address here, ending in 148, is the same one as F1 up here. right? And again, it's going to modify the B value, print it out like this, and exit, and you see the destructor get called again of the temporary that it made for the tenure of that call. And like a fool, I did not put in a last dump of F1, which would show us that neither of those calls will have modified the value in F1. Let's give us some space here. So we run it again. We see we create F1. It's 99 and 88. We made a copy up here and changed its contents, print them out. We passed it by value, printed it out, pass it by value, printed it out. Both of these calls to that function modified their copy of both F2 and F1. And when we're done, we printed out F1. We can clearly see that nothing modified F1. And again, we see the F2 and the F1 destroyed down there. So we can forcibly cause the copy constructor to be called by just explicitly calling it like this. We can infer that a copy is made by passing an object by value to a subroutine like this. Member functions or regular old functions, doesn't matter. If we need to make a copy of something to pass it somewhere, the copy constructor will be called. Well, there's another case where we see copies being made. Let's look inside here. Let's do a diff between number 3 and number 4 here before we move on to it. So the only difference we're going to see here between number 3 and 4, well, we're going to see the differences in the changes that I added just now to CopyCon 3. But CopyCon 4 has these additions down here. So specifically, we're going to see that we're going to make an assignment during a construction, all right? So this one here, the essence of this one is this was the same as number 3 until I added the extra printout down here, which we don't really need to see anymore. This one's going to create a copy of F2 while it's constructing F3. Having a single equal sign in there like that is exactly the same thing as this, okay? That's the whole point of this example right here. But this is only true during an assignment when you are constructing F3, okay? This is an optimization that the compiler gives you. Otherwise, an assignment is a whole different ballgame, all right? So I'm going to assign the value of F2 to F3 during its construction. It'll call the copy constructor. Then we'll just dump everything back out again like we saw before. Let's run number 4 here. Let's give ourselves some room. And we see F1 as we did before. We see it copying it when creating an F2 here. We see the 2 times it makes copies to call the func subroutine up there. And then down here, you can see the copy constructor getting invoked because we assigned the value of F2 to F3 while we constructed F3. And we can see that the value of F3 here is the same as the value of F2 down there. All right, and of course, F1 is left unchanged. Because we now have 3 local variables, we see 3 destructors all going on at once. All right, so when else can this happen? Well, we can also see it happen if we return something by value from a subroutine. Let's do a diff on this to make sure we all follow along. Diff, what do we got? CopyCon 4. Versus CopyCon 5. This is actually going to have a lot of differences in it here because what I've done in version 5 here is I've added these 2 functions, right? I've created a func2 up here and a func3. And you can see that func2 has no arguments and it returns a foo by value, all right? Func3 also returns a foo by value, and it works differently. 2 different ways to do this. And then there's some noise here about the differences between the main programs and the 2 subroutines. So let's look at CopyCon 5 here. So we know the only differences are that I've added these functions and rewrote the main. So let's look at these functions here. So this one up here is the same as we saw earlier on. that just simply dumps it out and returns. Func2 is one of them that can return a foo by value. And now I point out in this comment here, this example here will depend very heavily on the ability of your compiler to optimize this code. And we'll see that the compiler that I'm using right now does optimize this code, and it won't actually make a copy, which is a real, head scratcher. All right. But it can, due to a unique in certain situation. All right. This one down here won't have it so easy. Anyway, let's look and see what's going on in here. This function creates a foo. It sets some values in there. It dumps it out, prints some stuff, and it returns foo by value. All right. Now, there's a trick that the compiler is going to do in this particular case where the caller is going to pre-allocate a space to put it in there. This is a lot of hand waving and compiler optimization, but I wanted to show it to you because if you decide to run some experiments on your own, this can fool you. The compiler, in the most trivial case like this, can optimize that copy away. All right. This one down here is less likely to get optimized away. In this case, we're going to call func3. We're going to pass func3 a reference to a foo and an integer value. It's going to work very much the same way, but we're going to explicitly call the copy constructor. Then we're going to set the value of the b variable based on this parameter that we're going to pass in. We're going to dump it out, and then we're going to return that one by value. This is more complicated by the fact that we have manually created an F2 object in the middle of this function. In order for this to work, it's going to have to make that copy, all right? And the main down here, what's this one going to do? I've removed some noise, so all we're going to do is print out F1 like we did before. We're going to create an F2 by using the copy of what comes back from func3 over here, right? Remember, this returns one by value. We're going to use that value as the data to construct this F2 over here. Later on, what are we going to do? We're going to call func3 again, and we're going to pass it a reference to F1, which it's going to use to make a copy, and it returns that copy by value. And since this expression right here represents an object of type foo, because that's what func3 returns, we can take this and say dot and put a member function call in there. This will call getB on the foo object that is returned by value from func3. Then we'll print some asterisks and we'll print out F1 again and go on our merry way. So let's see how that one works. All right, I guess we don't have to compile it. So what does this guy do? He's going to create and dump out the F1 like we've been doing all along. And func3 is going to create a new foo using the copy constructor explicitly. We can then dump out the F2 here. We see that func3 has exited. And we can see that the func2 in main also has the same values. All right, so this thing ended up with the same values. Now look very closely. The address of this F2 in main is the same address as this F2 down here in the middle of the foo function. So this is the one where the compiler was playing some games with optimization. Let's not get too much into that. I just wanted you to see this so you realize that, there can be things removed from your program in non-intuitive ways if you're not looking at the bigger picture. Here's the other function, func3, all right? What is this thing all about? Well, remember, after we get back, let's look back at the main one more time to make sure we know what's going on. So we just looked at this up here, right? And we printed out some asterisks. Now what are we doing? We're printing out func3 blah, 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 equals... And we call func3 and call getB on whatever it returns, okay? So this is what's being printed out right now down here. Notice we start printing func3 blah, 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 blah equals. And right in the middle of that print statement, all of the output from func3 is printed right here. Right? And that makes a certain amount of sense because we call func3 right here while we're printing. So what happened? Well, it started printing all this, and then it calls func3, which means it's then going to do what func3 says, and that's print a bunch of stuff. Then it's going to call get b, and then print the value of b out, okay? And that's exactly what we see here. Here's a bunch of output with the equals. Here's the output that func3 prints while it runs. And here's the value of the b private member from the accessor, the get underscore b call that's invoked on this object right here, because clearly you can see that's the value of b in there. Now the destructor is called on the object that was returned by value. It's called right here. I didn't explicitly call it. Why did it get destructed right there? Well, notice that I never save the copy that was returned back from func3 anywhere. I simply called this get b on it right there. And when this print statement is completed, that value, that foo value, goes out of scope. Its scope is essentially the duration of this one statement, all right? That's why this destructor gets called right down here. So it gets constructed, used, and destructed all at once in the middle of that print statement. When that gets done, you know that I called dump on F1 again to make sure that we didn't modify it in any way, and we can see we did not, and then the F2 and the F1 again are destructed. All right, I know what you're saying. If the copy constructor just makes copies, what's the point? Well, let's look at a more complicated example here. What do we got going on in here? Let's say we have a pointer inside of our foo. All right, so what I've done is I've added this pointer variable, and I've also added a num_p value. All right, so the idea here is this class inside of it is going to have a pointer to an array of integers. And this num_p down here is going to remember how many there were. Okay? How are we going to use that? Well, by default, it's null, and there are none anyway. So these constructors don't care. We're going to just let the default values ride. Okay? This down here, we have to remember to delete the contents of that array. Because when this object goes away, this pointer will go away, and the program will have no way of remembering then where that array was. All right, so we need to remember to delete it down here. Now, it turns out that it's actually okay to call delete on a pointer whose value is null pointer. Delete checks for that, okay? So this is always safe to do, all right? Even though if I just construct this and then immediately destruct one, this does not have a valid array that it's pointing at, okay? So this is explicitly allowed in the specification for the language. So we're safe in that regard, all right? These are the same as they were before, and I've added a set p. Let's look and see how set p works. Well, we're going to grab the, what do we got? We got the size and then a pointer to an integer array. So presumably this is going to be used to allow the foo object to make a copy of the contents of an array that's pointed to by pi over here. So what do? We remember how many elements are going to be in the array, and we make an array of our own that's big enough to hold the n elements that we've been passed in. Then we write a simple little loop, and we go through there, and we just say my array of element number I equals the passed in array of element I. We just make a copy of it, all right? Then down here in our dump, I've added some more output so that we can see the num_p, and I wrote a nice little loop that prints out the contents of that array with the proper spacing and commas between the elements so that it's clean. And then I use it like this. What do? I create my F1 like I always do. Then I call the set p, and I say, I've got 6 elements in an array called A, which you can clearly see up here has 6 elements in it. And then I call dump on F1. Well, let's make sure that works. All right. What do we got? We construct a foo. It's sitting here at B780. We dump it out. And before I called set P, the pointer, and well, the number of elements is 0, and the pointer is also 0. And my little print routine has nothing to print, so it just prints the curlies with nothing inside it. All right. I remember I then called set P, and I gave it 6 elements of an array, and called dump again on F1. We see that it's still the same object at the same address. And this time numpy is 6, and the P does not have 0 in it anymore. It has some other address. It's pointing now at an array of 6 integers that the object foo allocated out of the heap, and within which it made a copy of the array that was passed in. All right, and those are the values of that. All right, so what does this have to do with a copy constructor? Well, let's have a look-see at example number 7 here. First, let's do a diff between 6 and 7 to summarize what changed. 6 and number 7. Absolutely, the only thing different is I'm going to make a copy of F1 into a new foo called F2, and then I'm going to dump out the F2, all right? So let's look at number 7 here, all right? The only difference is I'm going to do this. And notice that we're using the default copy constructor. Why? Because I removed it. There is no copy constructor. I did not write my own. Remember, this digression that I'm on right now was caused by me asking the question, why bother creating a copy constructor if you're just going to do a member-wise copy anyway? Okay? Well, here's what the default one will do if you don't provide your own in this case. First of all, we can see it died. That's not a good sign. What did it do before it died? Okay, it created F1 as it always does, just like it did last time. And it dumped out F1. It then assigns F1 the 6-element array. It then constructs F2 by making a copy of F1. And it calls dump on that, and we see its contents. And then it destructs. What is it destructing? It's destructing something at 1700, which is F2. All right. Then it destructs something at 16E0. Well, that's F1. While it was destructing F1, it says double free detected. And it dies. Why? Well, look what's going on here. F2, when the member-wise copy was done, the P pointer has the value that F1 has. So both F2 and F1 are both pointing at the same array at the same time. They both end in 92C0 over here. Okay? And when we destruct F2, it doesn't matter that F1 is the one that caused it to die. Whatever the second one is will cause this problem. Because they both point at the same array, when we destruct the first foo, which in this case was F2, it calls delete P in here. And it frees up that one copy of that array. Then when the other foo is deleted, which in that case was F1, it tries to delete the same array that's already been deleted. That is not okay. All right? Now, there's a lot of ways to fix this problem, and usually it's up to an application to ultimately determine how to do it. One way to do it in a naive type of program like this is to provide a proper copy constructor to make a copy of that array and not share. Not have two objects share the same one. So let's look and see the differences between CopyCon 7 and CopyCon 8. Well, the only difference between these two is I remove the message that's no longer true in version 8. And in 8, I add a proper copy constructor. Let's see what's going on here. No difference from what we saw before. None at all. I simply add this one call and a couple of comments about it right in there. Look, I'm going to use my own mutator to make a copy of P right in the middle of my constructor. And I note this is okay, provided that if you call your own member functions, that they're fully prepared to operate successfully, even if the object is not entirely yet done being constructed. This is not always something you can do, all right? In this case, it is. Let's look and see what's going on. A quick refresher here. Here's my constructor. Here's my call to set P. Remember, what set P does is it says, I need a pointer to an array of integers, and I need to know how many there are. When set P runs, it creates a new array, stores a copy of the count, and then copies all the elements. Now, this is okay in this object at this time, mainly because this set P doesn't use any of the local variables for any reason. It only sets the P and the num_P variables, the member variables in the foo object, and doesn't use any other ones. If it needed like the A variable up here or the B or something like that, and if I did not yet set them before I called this, then I'd have a problem, okay? You need to make sure enough of the object has been constructed by the time you call set P if it has dependencies on other members. That is my whole point here, all right? And yet, now you have this control because these are all member functions of foo. You know exactly what's going on because your foo object is responsible for itself, okay? So when you call a function like this, you're cognizant of the state of the object at the time that it's going to do these operations, okay? So let's go ahead and run then copycon 8 and see what it does. Let's clear this screen out here. All right, so what do we got? We make our F1 and we print it out just like before. We see it's empty. We then call set P and we set these 6 elements and dump it out a second time. And we see that we've got our 6 elements. Note the array that F1 has, the copy of, is sitting here at E2C0. Then we make a copy using our copy constructor to construct F2 over here. And F2 is constructed at C750. Specifically, that's different than F1, right? So this is a completely different thing in a different place. And we then dump it out. We have our same values in here, same. This F2's P variable has a different value than the P variable in F1 because we've explicitly allocated a different array and explicitly wrote a loop to go in there and copy these 6 values into here. Now, when the destructors are called on these two, of course, it works fine because the delete, when it deletes F2, is deleting an array that's at this address, and when the delete gets called for F1, it's deleting the array at this other address, all right? Now, this is called a deep copy. So terminology walk away here is shallow copy is your member-wise copy, all right? If the members as is are just copied, and that's actually quite fine in many cases to use a regular old member-wise copy, a shallow copy. That's actually why the compiler provides it for you by default. Didn't do that to purposely screw things up. It turns out quite often that's perfectly fine. But it's not always fine, as you can see in the case where we create our own dynamically allocated array for this P variable. We need to take responsibility for managing that. Now, you can have both F1 and F2 share the same copy of this array. They can both point to the same array. But you're going to have to keep track of how many times you refer to that array if you need to ultimately delete it, all right? It may be that your destructor never deletes it. and it should be deleted by something elsewhere in your program. That is completely up to the application design. So what's the takeaway? The copy constructor can be used in the following cases. 1, when an object is returned by a value, from a function. We saw that. It doesn't always have to happen then, right? Because the compiler can optimize these things away. Be careful when you run your little tests to verify this. 2, when an object is passed by a value as an argument, all right? Not when we're doing references, not when we're doing pointers, right? But if you ever pass an object by value as an argument to a function, there will be a copy made. When an object is constructed from another object of the same type, right? That's a long-winded way of saying, if I'm ever going to do this, right? F2 is F1, right? Copying it like this. Or, as you saw, if I put an equals an assignment in the definition of F2 like this, it will be copied using the copy constructor in order to implement those two statements, lines of code. And also, you'll see that the compiler sometimes needs to create a temporary object. Usually this will happen when we're dealing with what we call overloaded operators, which is a subject of a different discussion. And you're performing some like mathematical or logic operation on something that involves these objects. If the compiler needs to create a temporary, a copy of some variable in order to manipulate it in some way, it will definitely have to create a copy using the copy constructor, all right? Again, this one we'll see once we get to more advanced topics. But these three here, I think were demonstrated fairly well in this lecture. So, thanks for watching. See you next time.